In the previous lecture, we have discussed in detail the LS coupling, and in the discussion of LS coupling, you have seen that LS coupling takes place generally in case of the lighter atoms. Just in opposite manner, here you will see that this JJ coupling in general takes place in heavier atoms, or in other words you can say that the heavier atoms are governed by JJ coupling. In fact, this JJ coupling takes place when the spin orbit magnetic interaction dominates over the residual electrostatic interaction and the spin-spin correlation. As you know, basically there are three perturbation terms in the total energy of the atom, and those three terms are spin orbit magnetic interaction, residual electrostatic interaction, and the spin-spin correlation. So in this case, actually when the perturbing term spin orbit magnetic interaction is much greater than the residual electrostatic interaction and the spin-spin correlation, then actually the splitting of energy level takes place due to JJ coupling. Okay. So in this case, when you want to find the splitted energy level due to JJ coupling, you have to consider the perturbation term in this manner, or in this order you can say. First of all, we will consider the perturbation term spin orbit interaction. Actually, during a spin orbit interaction, the different orbital angular momentum vector L and the spin angular momentum vector S of individual electrons are added together vectorially and give the resultant angular momentum of the electron. Okay. So in this way we get the total angular momentum of an electron by adding vectorially L and S. And after that, residual electrostatic interaction and spin correlation takes place, and in this case actually the different J values of the individual electrons get added together relatively in less strongly, and then we get actually the total angular momentum capital J of the atoms. Okay. So now let us see how these two processes takes place and how an unperturbed energy level gets splitted into the different energy levels during the JJ coupling. So let us consider the first perturbation term, which is spin orbit interaction. And as I have told you that due to this spin orbit interaction, the orbital and the spin angular momentum vector L and S of each individual electron are strongly coupled together, and due to this coupling we get the resultant angular momentum, this is small j, of each individual electron. Mark this. This small j represents the total angular momentum of a particular electron, not of the atom. Okay. So the total angular momentum of an electron is given by a small j equal to a small s plus a small s. Mark this. A small j, this is the total angular momentum vector of an electron. L is the orbital angular momentum vector of an electron, and S is the spin angular momentum vector of that electron. So if the atom consists of a large number of electrons, then for the first electron you will write the total angular momentum vector by the symbol J1, and that will be equal to vector L1 plus vector S1. Similarly, for the second electron, J2 will be equal to L2 plus S2. Okay. Actually, the magnitude of this total angular momentum vector j of a particular electron is quantized, and its quantized value is given by this formula. From quantum mechanics, this result actually appears that modulus of j is equal to j times j plus 1's square root times h bar, where actually this j is actually known as the total quantum number. Mark this, total quantum number. When you write vector j, then that represents the total angular momentum vector. And if you write a small j, not the vector sign, then it represents just a quantum number. And this quantum number is actually a combination of the orbital quantum number L and the spin quantum number S. And this total quantum number J is given by L plus minus S. L plus minus S. Or you can also say that this is equal to L minus plus S, minus plus S, minus plus 1 by 2, because S is equal to 1 by 2. Because S has a fixed value, you know, this is equal to 1 by 2, but L will have different values. So for an electron, this J will have actually two values. First one will be L minus 1 by 2 and another will be L plus 1 by 2. Actually, this smaller value of J represents the lower energy level, and the larger value of J represents the higher energy level. And again, I am telling you, but you have learnt these things in the earlier classes. For electron in s orbital, this L is equal to 0. For electron in p orbital, this is equal to 1. In d, for the electron in d orbital, this is equal to 2. And for f, this is equal to 3, and so on. Okay. So let us illustrate this fact by taking a proper example here. If you consider an electronic configuration 2p, it means electron is present in the 2p subshell. Then as I have told you that for the p electron, L is equal to 1 by 2 and S has the fixed value. This is equal to L is equal to 1 for p electron, and S is fixed and it is equal to 1 by 2. So J will be what? J will be 1 plus minus half, or you can say this is equal to 1 minus 1 by 2 and 1 plus 1 by 2. 1 minus 1 by 2 is 1 by 2 and 1 plus 1 by 2 is 3 over 2. So J will have actually two values in this case. First one is 1 by 2 and another is 3 by 2. And as you have seen that the smaller value of J represents the lower level, so J equal to half represents the lower energy level, and J equal to 3 by 2 represents the higher energy level. Okay. So this is all about the spin-orbit interaction. In nutshell, you can say during the spin-orbit interaction, what actually takes place? Actually, for each individual electrons, consider these are the electrons, and the value of L for this is L1 and S is S1. For this second electron, L is L2 and S is S2. So first of all, this L1 and S1 get combined. This L2 and S2 get combined, and their combination actually gives J1 and J2. Okay. And J1, J2 are found by the formula L plus minus S, where S has a fixed value and that is equal to 1 by 2. And after this spin-orbit interaction, now you can see that each individual electron has different J values. Let us consider the first electron has J equal to J1. This is the total angular momentum of the first electron. This second electron has the total angular momentum of J2, and this third electron has the angular momentum, let us say J3, and so on. Okay. Now, the another two interaction takes place, and those perturbation terms are what? Those are actually residual electrostatic interaction and the spin-spin correlation. And due to these two interactions, actually the different J, that is the angular momentum of the individual electrons, that is J1, J2, J3 and so on, are added together. They are coupled, and they are actually coupled less strongly with respect to the spin orbit interaction. And due to the coupling of these J1, J2, J3, we get actually the total angular momentum of this electronic system, that is the atom. So when you will add vectorially these J1, J2 and J3, then you get the total angular momentum of the atom. Mark this. And that total angular momentum of atom is denoted by the symbol capital J vector. Capital J represents the total angular momentum of the atom, and a small j represents the total angular momentum of a particular electron. Are you getting the things or not? Okay. So the total angular momentum of the atom will be equal to capital J, and that capital J is equal to vector sum of these small j's, that is J1 plus J2 plus so on. This gives actually the total angular momentum J of the atom. Okay. In brief, you can write that this capital J, which is actually the total angular momentum of the atom, is equal to summation over I Ji, where Ji represents the total angular momentum of each individual electron. Mark this. A small j is the total angular momentum of each individual electron, and this capital J represents actually the total angular momentum of the atom as a whole. Okay. Just like this small j, you have seen that the total angular momentum vector of an electron is quantized. Similarly, the total angular momentum vector, this capital J, is also quantized, and it is governed by the same quantization rule. Actually, the magnitude of this capital J, which is the total angular momentum of the atom, this is given by a square root of capital J into capital J plus 1 times h bar. Okay. Here, this capital J is not the magnitude of total angular momentum. When you write that magnitude of total angular momentum, you have to write this symbol, because this is just confusing because symbol is same. You have to write mod of J. When you write mod of vector J, that represents the magnitude of total angular momentum of the atom. And this capital J, without the vector sign, without the arrow sign, represents actually the quantum number. And this total, this is called total angular momentum quantum number. Okay. Now you can see that this small j, which represents the total angular momentum of a particular electron, or you can say that the total quantum number for a particular electron. This quantum number j, small j, is always fractional. It is always half integral. Okay, it is always half integral. Mark this. But, and why it is always half integral, you can see, since j is equal to L minus plus s, and this is equal to L minus plus 1 by 2. And since L has only integral values, this L is 0, 1, 2, 3, 4 and so on. So definitely when you will add or subtract 1 by 2 from an integer, then definitely you will get half integers. Okay, half integral values. So J has only half integral values. But you will see that this capital J, which is the total quantum number of atom, this will have always integral value. This will have always integral value. We will see here. Now, what will be actually the values of this capital J, that is the total quantum number of an atom. In fact, the total quantum number J of total quantum number J of an atom has values from J minimum to J maximum at a step of 1. It means, first of all, we will find the minimum value of this modulus of J1 plus J2 plus so on, and then we will find the maximum value. Maximum value is simply the sum of these small j1 plus small j2 and so on. And you have to write all the numbers at a step of 1 from this j minimum to j maximum. Okay. So as you have seen that when the spin orbit interaction takes place, then an unperturbed energy level is splitted into the different energy levels, and after that, when this interaction, that is the residual electrostatic interaction and the spin-spin correlation takes place, when you get this capital J, then again those splitted energy level again gets splitted. Okay, what I am telling you, that will be crystal clear after this example. So let us illustrate this fact by taking a very simple example. Let us consider an electron configuration 4p4d. This is just an energy level when there is no perturbation applied on the atom. So you can say that this 4p4d represents an energy level or an unperturbed energy level. This is only one energy level. But in how many energy levels this 4p4d energy level will be splitted, we will see here during the JJ coupling. So let us first of all consider the spin orbit interaction, because you have seen that this JJ coupling can be dealt in two steps. First of all, we will consider the perturbation spin orbit interaction. So if we consider this example of 4p4d configuration, then for p electron, for an electron in 4p subshell, we will write the orbital angular momentum of the electron L1 is equal to 1, and this is actually the orbital quantum number, you can say, and the spin quantum number is 1 by 2. So the total quantum number of this electron present in 4p subshell will be what? This is J1, and that will be L1 minus plus S1. And S1 is fixed, you know. So, and as for p electron, L is equal to 1. So this will be 1 minus plus 1 by 2. And therefore, you can easily see that J1 will have two values. First one is 1 by 2 and another is 3 by 2. Okay. Now, for the d electron, L is equal to 2 and S is equal to 1 by 2. I have written the symbol L2 and S2, but these are values of L and S. So the value of J for this d electron, which I have written here J2, will be what? This will be 2 minus plus half. So 2 minus half, this is 3 by 2, and 2 plus half, that will be equal to 5 by 2. So you can see that actually for this configuration 4p4d, there are 4 different values of this small j. J1 has actually 2 values and J2 has also 2 values. So as a whole, there are 4 values of this small j. Okay, and when these J1 and J2 will get combined due to the residual electrostatic interaction and the spin-spin correlation, then what will be the combination you can see. Actually, we can combine J1 equal to 1 by 2 and J2 equal to 3 by 2. Okay, so there will be a combination of 1 by 2 and 3 by 2. Again, we will combine 1 by 2, that is J1 equal to 1 by 2 and J2 equal to 5 by 2. So this will be the another combination. Then we will combine J1 equal to 3 by 2 and J2 equal to 3 by 2. So this will be the third combination. And finally, we will combine J1 equal to 3 by 2 and J2 equal to 5 by 2. So this is the fourth combination. So you can see that this J1 and J2 will combine to give the total angular momentum J of the atom, and there will be actually the 4 combinations, and these are actually the 4 combinations. Now, for each combination of J1 and J2, now we will find the what will be the value of the total quantum number capital J. Let us see. Okay. Now, as I have told you that actually the smaller value of J represents the lower energy level. So in these 4 combinations, the combination 1 by 2, 3 by 2, that is this first combination, will be the lowest energy level, and this combination, that is 3 by 2 and 5 by 2, this will be actually the highest energy level. Okay. Now let us see this figure. I have shown this by this splitting by this diagram. You can see this is your unperturbed energy level 4p 4d. This horizontal line, which is I am just marking, this represents actually the unperturbed energy level. Okay. Now, due to the spin orbit interaction, you have seen that this energy level is splitted into 4 energy levels. Those 4 combinations of J1 and J2 represent the 4 different energy levels. Okay. And as I have told you that this 1 by 2 and 3 by 2 combination is the lowest energy level, and the 3 by 2, 5 by 2 combination is the highest. So after a spin orbit splitting, we get these 4 energy levels, which I have marked here. This lowest horizontal line represents the combination 1 by 2, 3 by 2, and this horizontal line marks the this is for the combination 1 by 2, 5 by 2, and you can see the other energy levels. So due to a spin orbit interaction, this unperturbed energy level 4p 4d has been splitted into 4 energy levels. Okay. Now, when the J1 and J2 will combine, we will get capital J, and the number of capital J obtained will represent the different energy levels. So these 4 energy levels again get splitted due to the residual electrostatic interaction and the spin-spin correlation. And what will be actually those energy levels, and how many energy levels in which these combinations will be splitted, you can see. Let us see. The first combination is what? The first combination is J1 equal to 1 by 2 and J2 equal to 3 by 2. See here. Now, if J1 is 1 by 2 and J2 is 3 by 2, we have to find the total quantum number capital J due to the coupling of this J1 and J2. And as I have told you earlier, if you want to find the total quantum number J and by the combination of a small j1 and a small j2, first of all we will find the minimum value of capital J. You know, minimum value of capital J will be what? That will be equal to 3 by 2 minus 1 by 2, and that is equal to 1. And then we will find the maximum value. Maximum value is simply the sum of j1 and j2. Okay, and that will be 3 by 2 plus 1 by 2, which is equal to 2. Okay, so minimum value of J is 1 and maximum value is 2. Now, as I have told you, if you want to find the total values of this capital J, you have to write the numbers from J minimum to J maximum at a step of 1. So first of all, we will write the minimum value 1, and then we will add 1 in this value, and that will be 2. Since this is the maximum value, so this J in this condition has only 2 values, and those values are 1 and 2. Okay. Now, consider the second combination, and this combination is 1 by 2 and 5 by 2 here. Actually, this 1 by 2 is a small j1, and this 5 by 2 is a small j2. So to get the value of capital J by the combination of this J1 and J2, again we find first of all J minimum. You know, J minimum is what? This is the difference of J1 and J2. So this will be 5 by 2 minus 1 by 2, which is equal to 2. And then we will find J maximum. This is simply the sum of J1 and J2, and that is 5 by 2 plus 1 by 2, which is equal to 3. So you have to write the first of all its minimum value, which is 2, and then 2 plus 1, which is 3, and this is actually the maximum value. So there is no need to write other numbers. So J has only 2 values in this case. These are 2 and 3. Now the third combination you have seen that J1 is equal to 3 by 2 and J2 is also equal to 3 by 2. So in this condition, what will be J minimum? J minimum will be 3 by 2 minus 3 by 2, which is 0. Okay, and J maximum, this will be 3 by 2 plus 3 by 2, which is 3. So now you have to write the numbers from 0 to 3 at a step of 1. So first of all, we will write 0. Okay, then 0 plus 1, which is equal to 2, then 2 plus 1, which is equal to 3, and this is the maximum value. So what are the values of J? Values of J will be 0, then 0 plus 1 is 1, and 0 plus 1 is 1, and then 1 plus 1 is equal to 2, and then 2 plus 1 is equal to 3. Okay, so the values of J are 0, 1, 2 and 3. You can see for this combination of J1 and J2, this capital J has 4 values. It means this energy level characterized by this combination of J1 and J2, 3 by 2, 3 by 2, will be splitted after these two interactions in 4 energy levels. Okay, and the first combination, that is here 1 by 2, 3 by 2, this will be splitted into 2 energy levels characterized by the quantum number capital J, 1 and 2. And the second combination, this is 1 by 2 and 5 by 2. For this combination, you have seen that J has 2 values, 2 and 3. So this will be also splitted into 2 energy levels. So this first combination will be splitted into 2 energy levels. The second combination will be splitted into, this is splitted into 2 energy levels. This will be also splitted into 2 energy levels. And this third combination will splitted into 4 energy levels. Okay. Now see the last combination, that is the fourth combination, where J1 is equal to 3 by 2 and J2 is equal to 5 by 2. So to get the value of capital J, let us now find again J minimum. And J minimum will be what? This is 5 by 2 minus 3 by 2 and this is equal to 1. And J max, this is 5 by 2 plus 3 by 2 and this is equal to 4. So you have to write the numbers from 1 to 4 at a step of 1. So what will be those numbers? Those will be 1, 2, 3 and 4. First number is 1, then we will write 1 plus 1, that will be 2. Then we will write 2 plus 1, that will be 3. And then we will write 3 plus 1, that will be 4. Okay. So J has these 4 values. And since J has 4 values, it means the energy level obtained after the spin orbit splitting, this energy level marked by this combination 3 by 2 and 5 by 2, after the residual electrostatic interaction and spin orbit correlation, this will be split into how many energy levels? This will be split into 4 energy levels. Okay. So the complete splitting of this energy level by the JJ coupling is actually shown in this figure. You can see here. Again, see, this 4p 4d level is the unperturbed energy level. It means when there is no perturbation term applied or no interaction takes place, then this is your energy level. Okay. Now when a spin orbit interaction takes place, then you have seen that this unperturbed energy level is split into 4 energy levels. The first or the lowest energy level is marked by the combination of J1 and J2, 1 by 2, 3 by 2. The second is marked by the combination 1 by 2, 5 by 2. Third is marked by the combination 3 by 2, 3 by 2. And fourth one is marked by the combination 3 by 2, 5 by 2. So this single unperturbed energy level has been split in these 4 energy levels after a spin orbit interaction. Okay. Now you have just seen that when J1 is 1 by 2 and J2 is 3 by 2, just we have seen in that condition the value of capital J are 1 and 2, and this 1 is a smaller value, so this will represent the lower energy level, and 2 is the higher value, larger value, so this represents the higher energy level. So this energy level obtained after the spin orbit splitting is now splitted into 2 energy levels having the total quantum number J equal to 1 and J equal to 2. So I have marked here this 1 by 2, 3 by 2 combination actually represents the energy level after spin orbit splitting, and that has been splitted into 2 energy levels marked by the total quantum number J, and values of J are 1 and 2. Again, you have seen just now that when the combination of J1 and J2 is 1 by 2 and 5 by 2, that represents this second energy level, and this energy level after the residual electrostatic interaction and the spin-spin correlation has been split into 2 energy levels, because this capital J has 2 values for these combinations, and those values were 2 and 3. You have seen. Okay. So this is split into 2 levels. Again, you have seen that the combination of a small J1 and a small J2, which is 3 by 2 and 3 by 2, for this combination J has 4 values, and those 4 values are 0, 1, 2 and 3. So this energy level is split into 4 energy levels. Okay, and similarly the energy level obtained by the spin orbit splitting by which is represented by the combination 3 by 2 and 5 by 2. For this combination, again you can see here that J has, this capital J has 4 values, 1, 2, 3, 4. So this is also split into 4 energy levels. Mark, see here. Okay. So these energy levels has been obtained after the residual electrostatic interaction plus spin correlation. Okay, where actually the individual J's of the electrons get combined to give the total angular momentum vector capital J. So what you are seeing here, actually you can see that an unperturbed energy level 4p 4d has been splitted into as a whole 12 energy levels. Let us count this. 2 plus 2 plus 4 plus 4, this will be 12. So this 12, this unperturbed energy level has been split into 12 energy levels after the JJ coupling. Okay. So I hope you have understand this idea very clearly, and in your examination, if JJ coupling is asked to write the short notes on JJ coupling, you can write all these things.